All right. So our implicitly defined functions, what they are, and how we take the derivatives of them. Okay. So sometimes, as it says, a relation can be defined in terms of x and y, but not in a way that lets you separate out and make it just say y equals. These are valid things. We have lots of things in the world that operate implicitly like this. Certainly the orbits of planets and those kinds of things are not functions. And so to get the full picture, we need to be able to deal with those, and certainly we're interested in the rates of change and trajectories and things that go along with the planets, okay, and the other things that are flying around in space. All right, so we have the tools. We just need to refine our technique. This showing here is a graph of x cubed plus y cubed minus 9xy equals 0. Okay, and I don't believe that it actually stops at those endpoints. It probably continues on from there, although implicitly defined functions sometimes do unexpected and strange things. Okay, so we can see it certainly fails the vertical line test. When we do this, we can get graphs that look like this sometimes with parametric equations as well, and we've already figured out how to deal with that, but sometimes parametrics won't quite define these things either. And so the beauty is that, you know, if I went back to teaching this class even 10 or 12 years ago, we couldn't make these graphs. We didn't have a tool that would do them. And then I was playing around with the math tools on the Smart Notebook and figured out it actually would graph them, which was a very cool thing. But then Desmos does as well. So you've got a free, easily accessible program that will graph implicit relations for you. And it really is only possible because of the increasing computer speeds. It's a time-intensive thing and involves picking millions of points and plugging them in and seeing what you get. With speeds of computers, we can do that in a reasonable way. All right, so what we need to understand at the beginning is we're always thinking of y as being a differentiable function of x. So when we are doing these things, this is always a chain rule, okay? So with the y in here, we see x is equal to y squared, and yes, we could write that as y equals the square root of x, but we would lose some information because it's really positive square root of x and negative square root of x. We want to keep this in a single problem. Okay? So the thought process here is we're going to start, everything starts with x. X is our independent variable. These are not parametric, so we're not starting with a t. And the x is getting changed into a y. Okay, we're getting a y of x, so that becomes a y, and our y then is getting squared. Okay. And this then, what is y? Okay, and this is a y of, this is not y times, right? Okay. Well, the derivative of that is dy dx, or shortcut notation y prime. The derivative of x squared is 2 times something, and that something here is going to be a y. So multiplying those things together, the derivative of my y squared is 2y times y prime. I put the equal sign, derivative of x is 1, and I can solve for my y prime. Okay, y prime will be equal to 1 over 2 times y. Okay. The important thing again is this step. This step that changes an x into a y in the beginning is always going to be a part of what's going on here. Okay. So got to get used to seeing that there, and we'll show a number of different examples to that. This is our derivative is implicit here as well. It shows us the derivative in terms of the y, and if we could explicitly make this say y equals, I mean, if we just kind of to tie this together and make this more believable, okay, y equals plus or minus the square root of x. If we substituted that in for the y here, we get 1 over 2 root x, right, which is what we would say if we had the derivative of y equals the square root of x. We would have said that's 1/2 times x to the negative 1/2 power. Okay, so this really is the same thing, it's just more complete, okay? Because y squared equals x is a parabola that opens sideways. Okay, y equals the square root of x is just the top half of that parabola. We wanted the whole thing. Okay. Okay, equations of tangents to implicitly defined functions. So this is, we recognize this as an ellipse. What is different about this ellipse than the ones that you studied before is the ones you did in pre-calculus either were vertical or horizontal, right? The major axis was either a horizontal line or a vertical line. This one has tipped. In order to tip that axis, we need a term like this that is happening in there that prevents us from being able to separate this out and say that it's either y equals or it is x equals. Okay. So this is the equation of that ellipse. They want us to find the equation of a tangent line when x is equal to -1. Well, we see those points are marked here. This right now at x equals -1. Those are the points. We can see those pretty clearly. If we put -1 into this equation, we could verify those points, because -1 squared is 1, and that'd give us a 1 plus y squared equals 7. So we could say y squared plus y minus 6 is equal to 0, and factor that into y plus 3 and y minus 2 equals 0, and say that's -3 or +2, and those are the y coordinates that are possibilities when x is -1. Okay, so we could verify the locations of those points even if we didn't have the graph to look at. Okay. Stick that up there and out of the way. And now we're going to do derivatives here. Derivative of x squared, that's easy, that's 2x. The derivative of -x times y, that's a product rule. Okay, so I'm going to start by saying it's a subtraction, certainly, and I'm going to do the first. The first is x times the derivative of y, which is y prime, plus the second, which is y, times the derivative of x. Derivative of x is just 1. So the derivative of xy is xy prime plus y. Okay, we're going to put it in parentheses because it's a two-piecer and we've got the subtraction out there. Plus the derivative of y squared. We did this on the previous screen, but I'll show it again here. We start with an x, we change that into a y, and the y then gets squared. So the derivative of the y is y prime. Derivative of this is 2 times y. So there is our derivative of y squared. Get that up there as well. And so that's 2y times y prime. Don't make this mistake. Don't say equals 7. We got to do the derivative on the other side as well. Derivative of 7 is 0. And so I'm going to distribute the negative through here, and we'll take a look at what we've got. We've got a 2x minus xy prime minus y plus 2y times y prime is equal to 0. And we want to make this say y prime equals. Okay, we should always be able to make this say y prime equals. The technique, normally I'd make you stare at this for a while, but that feels kind of pointless in this situation. I've got a y prime there, I've got a y prime there. I'm going to keep those. So 2y times y prime minus xy prime. And I'm going to move everything that doesn't have a y prime in it over to the other side. So I'll add a y over, I'll subtract a 2x over. And now I'm going to pull a greatest common factor out of this. Okay, and the greatest common factor is y prime. So I can rewrite this as 2y minus x times y prime is equal to y minus 2x. And so my y prime is going to be y minus 2x divided by 2y minus x. So there is my derivative. Okay. It says y prime equals. That's how I know it has a derivative. If I wanted the tangent lines, I can get two of them here. Okay. I know one goes through the point -1 comma 2. One goes through the point -1 comma -3. And so the slope, I should change colors on this. I'll make this one blue so we can keep track of what we're doing. And so I would just, if I evaluate this at the point -1 comma 2, I'm going to get a 2 plus 2 over 4 plus 1. Okay. That gives me a slope of 4/5. I think I believe that. It looks like it's fairly close to 1, but not quite. Okay. Along with those points, so y minus y1 equals m times x minus x1. There's my equation for the blue tangent line. Okay. If I evaluated this, oops, okay. If I evaluate this instead at the point -1 comma -3, then I'm going to get a -3 plus 2 over -6 plus 1, which gives me a -1 over -5. So that's going to give me a slope of 1/5. So my other equation is y plus 3 is equal to 1/5 times x plus 1. And those are my two different tangent line equations. Okay, this one is the equation for, in my famous curves index. If I look that up, this is referred to as the devil's curve. Okay. I don't know exactly why, although I know that we found a parametric version of the devil's curve that we tried to do. It's either parametric or polar. We tried to do on a graphing calculator, and it took an entire period for the graphing calculator to come up with anything close to what this was. And the weird thing was, points were just showing up randomly in different places. It wasn't like it drew a smooth curve. It was jumping all over the place. It was pretty wild. So let's do the derivative of the devil's curve, our y to the fourth. Again, if we want to do y to the fourth, the x gets changed into a y, and then that gets taken to the fourth power to give us a y to the fourth. So this is a y prime. This is 4 times y cubed. So this becomes a 4y cubed y prime. Minus 4y squared. Well, that's going to be minus 8y times y prime. We've done the y squared a couple of times now. Equals 4x cubed minus 18x. It's not a particularly challenging one. I'll factor out the y prime. get a 4y cubed minus 8y is 4x cubed minus 18x. So y prime is 4x cubed minus 18x over 4y cubed minus 8y. I could cancel a 2 out of everything anyway and call this a 2x cubed minus 9x over 2y cubed minus 4y. And that's what that derivative would look like. I think that when you graph this on Desmos, it might look slightly different. It might clean up some of that, the resolution higher on Desmos. But certainly a bizarre looking graph. I got one little normal thing looks like happening around the origin, and the rest of it is just all over the place. So let's take a look at the derivative here, because there's several things that are going on. And the way that I would represent this, first of all, inside of this tangent function, I've got a product. Okay? And so the only way that I can represent that is to say that this is not really a clean way to do that, other than to say, okay, I got an x times y squared. And the x times y squared I'm going to load into the tangent function. And to find this, I need to do a product rule. So I get first times the derivative of the second. There's my derivative of y squared again, which I recognize is 2y times y prime, plus the second times the derivative of the first. So that's the derivative of xy squared. And the derivative of tangent is secant squared of xy squared. So derivative of tangent of xy squared is these two things multiplied together. So I'll write that as a secant. Well, let me go ahead and distribute it through. So that's going to give me a 2xy times the secant squared of xy squared times y prime plus y squared times the secant squared of xy squared plus the derivative of 2x, which is 2, is equal to the derivative of 3y, which is 3y prime. Need to get everything with a y prime together on one side. So I'll keep the 2xy times the secant squared of xy squared times y prime. I'll subtract the 3y prime. And on the other side, then, I'll move my other pieces, which is going to be a -2 and a negative y squared times secant squared of xy squared. And then I factor out the y prime. So this gives me y prime times 2xy times the secant squared of xy squared minus 3 is equal to -2 minus y squared times the secant squared of xy squared. And then a little division, and I get y is equal to, or y prime is equal to, -2 minus y squared times the secant squared of xy squared over 2xy times the secant squared of xy squared minus 3. And I can't imagine trying to figure out slopes of tangent lines on something like that. First of all, trying to identify a point that I know for certain is on that graph to plug it in there and figure out what the slope of the tangent line would be there. Okay. And I believe that was the end of what I was going to talk about.